Otto cycle, the ideal cycle for spark ignition engines. Okay, Otto cycle is the ideal model for spark ignition engines or gasoline engines because the fuel used in these engines are gasoline engines, gasoline engines, and the gasoline is used as the fuel. So in this cycle, we will learn the operation of this cycle. Okay. So there are 4 strokes. It is called 4-stroke cycle, because there are 4 strokes. What is a stroke? What is a stroke? Stroke. What is a stroke? You can answer me by writing on the chat, or you can use your microphone. Okay, Gülis has the answer. Okay, Gülis says between top dead center and bottom dead center. She means the distance. Mohammed says the volume difference. Celil says the stage. Okay, the correct answer is the distance between top dead center and the bottom dead center. That is the stroke. 4-stroke cycle means in one cycle there are 4 strokes. 4-stroke distance, up to down 1 stroke, bottom to up 2nd stroke, top to bottom 3rd stroke, bottom to up 4th stroke. So there are 4 strokes, 4 movement. Okay, the first stroke is compression stroke. Okay, compression stroke. What is compression stroke? Compression stroke is the air-fuel mixture is compressed from bottom dead center to the top dead center. A. It is A. So this is the first one. Actual 4-stroke spark ignition engine and the compression stroke. Piston goes from bottom dead center to the top dead center. Can you see the pointer? Red pointer, you can see it, right? From bottom dead center to the top dead center. This is the compression stroke. Thank you for your answers. Okay. In the compression stroke, piston goes from bottom dead center to the top dead center. There is air-fuel mixture. The mixture is compressed. And on the PV diagram, process is this, from here to here. Okay, compression from here to here. From bottom dead center to the top dead center. Okay. After piston reaches the top dead center, this point just before top dead center, spark plug ignites. Ignition, this is the ignition point. At the end of the compression stroke, just before top dead center, here it goes. Here, there is an ignition, spark plug ignites. Okay. After spark plug ignites, piston goes and reaches the top dead center, and the pressure rises immediately. Volume is almost constant. This is the combustion process. From here until here, combustion process. Okay. From here, combustion starts after ignition, after spark plug ignites, combustion continues, finishes here. It starts just before top dead center, slightly before top dead center. It finishes slightly after top dead center. Pressure increases, volume is almost constant. Okay, this is this combustion process. Then piston goes from top dead center to the bottom dead center. This process, piston goes from top dead center to the bottom dead center, this movement. This is called expansion stroke or power stroke. Expansion stroke or power stroke. Okay. Then when the piston is here, before bottom dead center, right here, comes here, just before bottom dead center, at this point, exhaust valve opens. Which one is the exhaust valve? This one is the exhaust valve. It opens. Exhaust valve opens. And from here, exhaust gases goes out of the cylinder here. Okay. Because pressure of the exhaust gases are high, exhaust gases rush out of the cylinder immediately after exhaust valve opens. So this process is called from here until here exhaust blow down. Exhaust gases, 90% of exhaust gases goes out from here until here. This is exhaust blow down process. Then piston reaches bottom dead center. And after piston reaches bottom dead center, it goes towards the top dead center. This is the exhaust stroke, this process from here to here. Exhaust valve open and the piston goes from bottom dead center until top dead center. This is called exhaust stroke. Exhaust stroke. Okay. This is called exhaust stroke. And during exhaust stroke, piston goes from bottom dead center until top dead center. And slightly before top dead center, intake valve opens. Here intake valve opens. And air-fuel mixture enters. Air-fuel mixture enters. And air-fuel mixture enters here. And then enters, intake valve is open. Piston goes from top dead center to the bottom dead center. Piston goes from top dead center to the bottom dead center, and intake air-fuel mixture enters. They enter, and the piston goes from top dead center until bottom dead center. This is the intake stroke. After piston reaches bottom dead center, slightly after bottom dead center, so this is the intake stroke, intake stroke, intake stroke. It reaches bottom dead center, slightly after bottom dead center. Here, compression process starts. Intake valve is closed and the compression starts. So the cycle is completed. Cycle is completed. Okay, now I explained the operation of the cycle. Actual four-stroke spark ignition engine operation. Okay, based on my explanation, can you tell me the names of the cycle strokes? There are four strokes, right? Compression stroke, power or expansion stroke, exhaust stroke, and intake stroke. In each stroke, piston travels one stroke. Compression stroke from bottom dead center to the top dead center. Power stroke or expansion stroke from top dead center to the bottom dead center. Exhaust stroke from bottom dead center to the top dead center. And intake stroke from top dead center to the bottom dead center. During exhaust stroke, exhaust valve is open. During intake stroke, intake valve is open. Okay? Okay, there are four strokes, but I mentioned 6 processes. Which processes I mentioned in the operation, but they are not the stroke? Can you write that in the chat? Answer this question. Okay, so I explained 6 processes, but there are 4 strokes. Tell me what are the 2 other processes which are not strokes? Which processes are they? Answer it in the chat. I am waiting for your answer. I described 2 processes in the operation of the cycle, but they are not strokes. They are just process. What are they? What are they? Okay. What are they? Alperen and Mohammed has some answers. Anyone else? No answer? Okay. Now I will describe the process again and you will find my answer. I will quickly repeat the operation. Here, I will explain it here in the PV diagram. Here, compression stroke starts, piston travels from bottom dead center until the top dead center. Slightly before top dead center, spark plug ignites and the combustion starts. Combustion process continues slightly before top dead center, continues and finishes slightly after top dead center. This is the combustion process. Then expansion stroke or power stroke, piston goes from top dead center until here, bottom dead center. Here, slightly before bottom dead center, exhaust valve opens and most of the exhaust gases go out of the exhaust valve. This process is called from here until here, it is called exhaust blow down. Exhaust blow down. Exhaust valve is open and the exhaust gases are at higher pressure. Then here, after here, from bottom dead center to the top dead center, exhaust stroke, exhaust valve is still open, and slightly before top dead center, intake valve opens, and the intake air fuel mixture enters the cylinder. Then after that, you have the intake stroke, intake valve is open, piston goes from top dead center to the bottom dead center, and intake air fuel mixture enters during this stroke. Now let me ask you the question again. What are the two processes which are not strokes? Same question. Answer the question. Answer the question. Yes, the first one is correct, combustion process. Okay, what is the other process? Exhaust blowdown. Thank you, Kaan, Furkan. Thank you, guys. Furkan has better blowdown is together, Kaan, like Furkan wrote. Okay, good. Combustion and exhaust blowdown. Combustion occurs. When is the combustion? It starts slightly before top dead center. It finishes slightly after top dead center. Exhaust blowdown, it starts slightly before bottom dead center. It finishes slightly after bottom dead center. These are the timing of these processes. Okay, good. So this is the actual four-stroke spark ignition engine operation. Okay. And then we have ideal Otto cycle operation. When we model it, this cycle, we use an ideal cycle model. The ideal cycle is called ideal Otto cycle. And the operation of ideal Otto cycle is given by the PV diagram here and by the figure here. Here is the operation. From 1 to 2, isentropic compression in the ideal cycle. Piston goes from bottom dead center to the top dead center. Okay. Process 2-3, constant volume heat addition process. And we use air as the working fluid. And there is a heat addition to the air during process 2-3. 2-3 is constant volume heat addition process. What is the actual process for this? This constant volume heat addition process. What is the corresponding actual process? What is the corresponding actual process to the constant volume heat addition process? This constant volume heat addition process replaces which process, which actual process? What is this process in the actual cycle? This constant volume heat addition process. Wrong answers. Wrong answers. Wrong answers. Okay, so this is the constant volume heat addition process. Then you have the isentropic expansion as the piston goes from top dead center to the bottom dead center. Okay, 3, 4. And the 4-1, constant volume heat rejection process. Constant volume heat rejection process. constant volume heat rejection process. So this, in the ideal Otto cycle, 1, 2 isentropic compression, 2, 3 constant volume heat addition, 3, 4 isentropic expansion, 4, 1 constant volume heat rejection. 1, 2 isentropic expansion, in the actual cycle, this is normal compression of air-fuel mixture. Okay, here isentropic compression of the air here. Here, in the ideal cycle, constant volume heat addition 2, 3. In the actual cycle, this is the combustion process. 3, 4 isentropic expansion. In the actual process, it is expansion power stroke. 4, 1 constant volume heat rejection process. In the actual cycle, it is exhaust blowdown. Okay, so this is how they transfer. So the intake and exhaust processes here are not represented in the ideal Otto cycle because they cancel each other in the ideal Otto cycle. Okay. Okay, so four-stroke cycle, it is the one cycle, four-stroke, 2 revolution, right? In the four-stroke, there are 2 revolutions. There is also two-stroke cycles. In the two-stroke cycles, there are 1 cycle, 2-stroke, and 1 revolution. Okay, four-stroke cycle and the 2-stroke cycle. 2-stroke cycles are used in automobiles, and here is the operation of a 2-stroke cycle. Let's go over the operation of 2-stroke cycle. So there are 2 strokes in the 2-stroke cycle. One is compression stroke, one is expansion stroke. First, you have the compression stroke. Here, there is air-fuel mixture here, and the piston goes from bottom dead center to the top dead center and compresses air-fuel mixture. Then at the top, spark plug ignites and the combustion process starts. During the expansion stroke, piston goes down. First, it uncovers the exhaust port, and then exhaust gases goes out of the cylinder. It goes down further, and it uncovers this port where intake air-fuel mixture enters into the cylinder. Then the piston continues to go down, reaches the bottom dead center, then goes up. First closes this port, then closes this exhaust port, then the combustion process starts. This is the operation of 2-stroke cycle. In the 2-stroke cycle, the intake air mixture entering here during the expansion stroke is called intake scavenging. And when the piston goes down, exhaust gases goes out of the exhaust port here, which is called exhaust scavenging. And during intake scavenging and exhaust scavenging, there is a period of time for which both exhaust and intake ports are open. During this period, some of the intake air-fuel mixture goes out of the exhaust port. This is not only the waste of fuel, but it is also a source of air pollution. Okay. This is the operation of 2 strokes. In the 2-stroke cycle, there is 1 cycle, 2-stroke, and 1 engine revolution, 1 revolution of crankshaft. In the 4-stroke cycle, 1 cycle, 4-stroke, and 2 revolution of the crankshaft. Because 1 stroke is equal to how many degrees of the crankshaft rotation? 1 stroke is equal to how many degrees of crankshaft rotation? When the piston goes from top dead center to the bottom dead center, how much revolution the crankshaft is? What is the revolution, rotation of the crankshaft? Anyone else other than Muhammad? 1 stroke is equal to how much crankshaft rotation? Yes, 180 is the correct answer. Thank you, guys. 1 rotation, 1 stroke, 180 degrees of crankshaft rotation. 2 stroke, 360 degrees, 1 complete revolution. 4 stroke, 360 degrees. 4 stroke, 720 degrees. Okay, so 4 stroke, 1 cycle, is equal to 4 stroke, 2 revolution. 2 revolution is equal to 720 degrees. 1 stroke, 180 degrees. 2 stroke, 360 degrees, which is equal to 1 revolution. And 1 cycle is equal to 2 revolution. And in a 2-stroke cycle, 1 cycle is equal to 2 stroke. It is equal to 1 revolution. This is the advantage of 2-stroke cycle. And as a result, in the 2-stroke cycle, you produce more power. Why? Because you have the combustion in every 2-stroke. So in the 2-stroke cycle, okay, 1 stroke, 2-stroke combustion. 1 stroke, 2-stroke combustion. 1 stroke, 2-stroke combustion. In 4-stroke cycle, 1 stroke, 2-stroke, 3-stroke, 4-stroke, then combustion. So here, start from here, 1, 2, 3, 4 combustion. 1, 2, 3, 4 combustion. So you have the combustion of the fuel in every 4-stroke, in 4-stroke cycle. In 2-stroke cycle, combustion, 1, 2, combustion, 1, 2, combustion. In 4-stroke cycle, combustion, 1, 2, 3, 4, combustion, 1, 2, 3, 4, combustion. For that reason, in 2-stroke cycle, you produce more power because you burn more fuel in a given time. For that reason, 2-stroke cycles for a given engine size, theoretically twice as powerful. So you produce 100% more power from the 2-stroke cycle. Okay, any questions? Are there any questions? Are there any questions? Do you have any questions about the stuff that we discussed? Are there any questions? No? Okay. Are there any questions about the material I taught? If you have other questions, wait until the end of the lectures. Okay. No question. Good. Is this 2-stroke or 4-stroke? This lawn mower. 2-stroke, of course. Of course, 2-stroke. This is. Thank you for your answers, guys. Furkan Rahman Emir Arslan, welcome for your first answer. Okay. This is 2-stroke engines. Okay. Lawn mowers, motorcycles, model airplanes, they use 2-stroke engines. Okay, here, this is the TS diagram of the Otto cycle. TS diagram. We discussed the PV diagrams before, right? This is the PV diagram. This is the PV diagram of the Otto cycle. Process 1, 2, 2, 3, 3, 4, 4, 1. Okay, this is the TS diagram. In the TS diagram, 1, 2 is isentropic compression. 1, 2. Isentropic means entropy is constant here, reversible and adiabatic. 2 to 3, constant volume heat addition. 3, 4, isentropic expansion. 4, 1, constant volume heat rejection. Okay, so these are the 4 processes for the ideal Otto cycle. Okay, in this ideal Otto cycle, intake and exhaust strokes are included. Here, the cycle is like this: 0, 1, constant pressure intake process, 0 to 1. Piston goes from top dead center to the bottom dead center, 0, 1. Constant pressure heat addition, 0, 1. Okay. 1, 2. Isentropic compression. 2, 3, constant volume heat addition. 3, 4, isentropic expansion. 4, 1, constant volume heat rejection. 1, 0, constant pressure exhaust process. during 0, 1, is the valve are open or closed? Intake valve during 0, 1, intake valve is open or closed? During process 0, 1, intake valve is open or closed? Okay, the correct answer is open. Thank you guys for your answers. It is open. From 0 to 1, intake valve is open. Intake air-fuel mixture is entering, and the pressure is constant. 1, intake valve is closed. Isentropic compression, heat addition, isentropic expansion, heat rejection. 1 to 0. What can you say about the valves? In 1 to 0, 1 to 0. What can you say about the valves? Which valve? Onur. Yes. Yes, you are correct, guys. From 1 to 0, exhaust valve is open. Exhaust gases are going out of the cylinder. But 0, 1, the work output during 0, 1, which is the intake process, which is the expansion, and the work input during 1, 0, they are equal to each other. So they cancel each other. As a result, this intake and exhaust processes has no effect on the cycle operation. Okay, good. Okay. Any questions? Okay. Okay. Do you have any questions? No, no questions. No questions. So let me go over the thermodynamic analysis of the cycle. Thermodynamic analysis of the cycle. Otto cycle. Otto cycle. Otto cycle. So guys, process 1, 2. What is the name of this process? 1, 2. Name of this process 1, 2. Process 1, 2. Okay. Okay, 1, 2 is isentropic compression. What is process 2, 3? 2, 3. 2, 3 is constant volume heat addition. What is 3, 4? 3, 4. 3, 4. Constant, not constant, isentropic expansion. And the 4, 1, what is 4, 1? 4, 1. 4, 1, what is 4, 1? Constant volume heat rejection. Okay. So the equations will be accordingly. So for any thermodynamic system, we have this general energy balance equation, Q in minus Q out plus W in minus W out is equal to internal energy change for any closed system. And we have a closed system here. Is this a piston cylinder device? So it's a closed system. During all the processes, it's a closed system. 1, 2, 3, 4, 4, 1, all closed systems. And we have the equations accordingly.